Dear ladies and gentlemen, welcome to today's webinar about calibration of a digital temperature sensor on the wafer using the example of the SMT172. My name is Robin Ellinger. I'm working for Angst+Pfister Sensors and Power as a product manager, and I'm responsible for the temperature sensors. On this slide I will show you the agenda for today. So first of all I want to show you who is Angst+Pfister Sensors and Power. Don't be worried, it's just a short introduction and will take maybe 30 seconds. Afterwards I want to show you the functional principle of the SMT172, which is our temperature sensor with a duty cycle as the output signal, and on basis of this I will show you the wafer-based calibration. The next step will be how are digital sensors evaluated and what are the most important parameters of temperature sensors. Afterwards I want to show you the advantages of digital temperature sensors, and last but not least I want to show you typical applications of calibrated digital temperature sensors and why the SMT172 has an extremely high response speed and a low long-term drift. I hope you enjoy it. And on the next slide I will show you who is Angst+Pfister Sensors and Power. So first of all, Angst+Pfister Sensors and Power is part of the Angst+Pfister group with 100 years of company history, 24 locations worldwide and around 2,000 employees. 40% of our products on the website are customized, which means that they are not standard items and they are customized for customer applications. Angst+Pfister Sensors and Power offers a lot of different sensors. So as you can see, we are offering temperature sensors, flow sensor, gas sensors, temperature sensors and many more. But today the focus will be on the temperature sensors, and as you can see on the right we have a temperature sensor. Like I said, it's a digital temperature sensor and the sensor is available as a TO18 housing, TO92, TO220 and many more. All of them are capacitor housings, transistor housings, sorry. Also we are selling humidity sensors, infrared sensors and customized temperature probes. The customized temperature probes are really nice because you can choose different cable length, cable material, isolation, the housing material, the sensor technology. For example, if you want to use our SMT172, that's fine, but we can also offer you customized probes with NTCs, PD100 and many more. On this slide you can see a picture of the temperature sensor, and then afterwards I will show you the functionality of the temperature sensor. But first take a look on the picture on the right, and there you can see a headphone and a view of the temperature sensors, and you can see that it's really small. The temperature sensor chip or die itself has a size of 1.7 meter times 1.3 millimeters, so it's really tiny. And if you take a look, you will see plenty of capacitors, resistors, a Schmitt trigger and 8 Zener diodes. In a few minutes I will show you what we are doing with the Zener diodes and how you could use them for calibration on a wafer. But first of all, I think the temperature sensor is really special because it's based on a 0.7 micrometer CMOS process, and the sensor is using BJT transistor to generate a duty cycle as an output signal. And like I said, a duty cycle as an output signal is really rare for a temperature sensor. But for some application, it's really nice that you have a duty cycle as an output signal because you are independent to resistance in cables. So for example, if you have the temperature sensor on one side of the room and the calibration, the measuring unit on the other side of the room, then it doesn't matter if you have 5 meters of cable length, and it will not affect the accuracy at all. If you take a look on this slide, you can see the functionality of the temperature sensor, but it's greatly simplified. So on the left side you can see two current sources. I1 has a positive temperature coefficient and I2 has a negative temperature coefficient, which means that if the temperature is rising, the current of I1 will rise also, and the current of I2 will sink. With the help of a switch, you can switch from I1 to I2 so that I1 doesn't have a function anymore. Also, you can see a capacitor and a Schmitt trigger. And after the Schmitt trigger, That's the output of the sensor. So one step back, as you can see, there's a capacitor, and the capacitor is charged via I1 and discharged with the help of I2. The capacitor has two values. The first one is V1, it's the lower charge value, and V2 is the upper charge value. And with the help of I1, you are charging the capacitor, which you can see here. And if the higher charge value is reached, then the Schmidt trigger will switch from 0 as an output signal to a 1 or high as an output signal. And in the same time, the Schmidt trigger will send a feedback to the switch, and the switch will switch from I1 to I2, which means that I1 doesn't have a function anymore, and we are discharging the capacitor with I2. So you can see it here. We are discharging the capacitor again, but the Schmidt trigger still have a high as an output signal. When we are reaching the lower charge value, then the Schmidt trigger will switch again to 0 as an output signal, and the switch will go back to I1. So we are starting to charge the capacitor again. So once again, the current sources have a positive temperature coefficient, which means if the higher the temperature, the higher the proportion of the highs. And therefore, you can calculate the temperature with the proportion. On the next slide, I will show you how we calibrate a temperature sensor directly on the wafer. As a next step, I want to show you how we calibrate our temperature sensors directly on the wafer. So first of all, if you take a look on the right, you can see a wafer, and it's a 6-inch wafer, which means it has a diameter of 6 inch. On each wafer, there are approximate 6,500 temperature sensors. And each of the sensors is precisely measured on a test device and compared with a reference at room temperature. Room temperature means that it can be between 20 degrees Celsius up to 28 degrees Celsius. It depends on the season. We are using Zener zapping for our calibration process, which I will show you in a second. So first of all, we have 8 Zener diodes that can assume the high or low state, and each of the 8 Zener diodes are on each temperature sensor. So if you take a look on the picture on the left, you can see that we have a resistor and we have a Zener diode on bottom. And below the Zener diode, we have a signal output, which we are measuring. So if we are not zapping the Zener diode, then it has a really high resistance, which means that the current is flowing to the right, which means that the signal on the bottom is low. But if we are zapping the Zener diode, then the Zener diode will have a short circuit, which means that it has a really low resistance, and the current is flowing to the bottom, which means that we have a signal high, which you can see here. Not zapped equals low, zapped equals high. And this means that there are 2 to the power of 8 possibilities, which equals to 256 calibration options. It's 2 to the power of 8 because we have each 8 Zener diodes, and each of the Zener diodes could have the output low or high. So that's 2 of the power to 8, which equals to 256 calibration options. This 8-bit signal allows the logic in the sensor to read this value, and for each value, once again from 0 to 256, a resistor is switched on to influence the voltage drop across the capacitor, which I showed you in the slide before. The capacitor generates the duty cycle as an output signal, and if we have a higher voltage drop on the resistance on the capacitor, then the capacitor will be charged faster, and therefore we can improve our accuracy because the capacitor will be charged a little faster. Once again, by zapping, the logic inside the sensor registers how many resistors should be switched on in addition, so that we can influence the voltage drop on the capacitor. If all 256 resistors are switched on, then we can shift the offset of plus 2 degrees Celsius. So in theory, we could have an accuracy up to 0.008 degrees Celsius, and that's really accurate, but it's only at room temperature. So on the next slide, I want to show you an example, and that's a question to you, so please keep attention. So if you take a look on the drawing on the bottom, then that's basically how it looks inside the sensor. So once again, we have 8 Zener diodes, and all of the Zener diodes could have the value high or low. If we are zapping the Zener diodes, then we will have the value high. And as you can see, none of the Zener diodes are zapped yet, which means that we have a binary code of 0, 0, 0, 0, 0, 0, 0, 0. And like I said before, if we zap all Zener diodes, then 256 resistors will be switched on, and we can shift the offset upwards by plus 2 degrees Celsius. But in this example, we have an offset of minus 1 degree Celsius, which means that we only want to switch on 128 resistors, because 128 in binary corresponds to 1, 0, 0, 0, 0, 0, 0, 0. So what do you think? Which or how many Zener diodes we have to zap to get this code in binary? I will give you a few seconds to think about it, and then I will show you the solution. All right. As you can see, we have to zap the Zener diode on the left, because like I said before, all of the Zener diodes have a 0 as an output signal, which means that if we want to have a 0 in the Zener diode on the left, we have to zap the Zener diode on the left. And therefore, the controller inside the sensor now switches on 128 resistors. The advantage of this calibration method is that we save ourselves a one-time memory cell, which is expensive, and also it takes a lot of time after restarting the sensor. And with the Zener diode zapping, we can save time when we are restarting the sensor, and we can measure immediately after restarting the sensor. So once again, if you take a look on the picture of the sensor, you can see that we have 256 resistors, and which you can see that all of them are vertically. And the controller now will switch on 128 resistors. As a next step, I want to show you how to evaluate the sensor signals of a temperature sensor. The advantage of a duty cycle as an output signal is the loss-free transmission of the measurement signals over very long distances. So it doesn't matter if you have 2 meters of cable length or if you have 8 meters of cable length. The sensor signal is always really accurate. This is not possible with an I2C sensor because interferences are too significant for the output signal. So if you want to have a sensor with really long cables, then I2C signal is not possible at all. But how exactly do you evaluate a duty cycle? The information is coded by the width of the pulse length in related to the period duration. So if you take a look on the top right, you can see the period length, and inside the period length you have a specific amount of lows and highs. And the higher the amount of the highs leads to a higher temperature. And the receiver, which could be a conventional microcontroller, demodulates the signal. So basically, the pulse width are measured and calculated using a formula, which you can see here. So basically, you're just measuring the time of the high and the lows, and therefore you can calculate the pulse length, and with the pulse length you can calculate the temperature afterwards. So it's basically really easy, but you need a microcontroller. But like I said, conventional microcontrollers are possible for this. So as you can see, the temperature sensor has a digital output signal, but also you can evaluate the sensor as you can use the sensor with an analog output signal. The sensor signal can be evaluated not only digital but also analog, like I said. The duty cycle can be converted to an analog signal directly at the sensor. All you need is a low-pass filter, which means that you are charging a capacitor again, which generates an analog output signal. Unfortunately, this output signal is rather inexact. So once again, if you take a look on the picture on the bottom, you can see that you have your output signal, which is a duty cycle, and if you have a high as an output signal, then you are charging a capacitor again, and that's your analog signal. On this slide, I want to show you how can different temperature sensors be differentiated and evaluated. Temperature sensors have lots of technical key features, but depending on the applications, only a few are relevant. It's the same with buying a car. For the father of a family, the number of seats are important, while for other factors are important. The most common key features for temperature sensors are the accuracy, the repeatability, which means that the system is set once, then the same result should always come up. The response speed, which is relevant for very fast temperature changes, so that you can detect the temperature change really fast. Then there's the resolution, the long-term stability and temperature drift, which could possibly save recalibration, and value usually differs greatly. So for example, like with our sensor, you have a temperature drift usually less than 0.01 degrees Celsius a year, while for other technologies, the temperature drift could be 0.5 degrees Celsius, which is a factor of 50 difference. So that's a lot, and possibly could save you a recalibration, which is really expensive. Also, there are different designs available, like SMT, transistor housing, different dimensions, and also different technologies. Also, there are different output signals available, like analog sensors and digital sensors, and also sensors have different self-heating, which means that if the sensor has a really high self-heating, then the accuracy will be low as well. Also, the price could be basically everything. There are sensors for a few cents up to several euros. It always depends on your application and on which key factors you need for your application. So to summarize, different technologies have different strengths. In the next step, I will introduce you to the strength of our digital temperature sensor, which is based on a semiconductor, using the example of the SMT172. So on this slide, you can see the advantages of temperature sensors which are based on a CMOS basis. And as you can see, the sensor has a really low self-heating and a really low temperature drift. The temperature drift depends on a few benefits of the sensor, which I will show you in a few slides. Usually, semiconductor sensors have a really high efficiency because they usually use an average consumption below 1 microjoule per measurement, and that's really low. So the sensors are really great for mobile devices like remote controls, mobile phones. So basically in all of the applications where you need a really high efficiency and you don't want to have a high energy consumption. Usually the sensors have also a very high reaction speed. Like I said, the high reaction speed is important for applications where you have really fast temperature changes. Usually the sensors don't need a recalibration because they are calibrated directly on the wafer and you don't have to recalibrate them, which could save you a lot of money. Also, sensors with a duty cycle as an output signal are available with really long cables because, like I said in a few slides before, that the cable length doesn't affect the accuracy of the sensor. So for example, if you compare it to a PT100 or PT1000, then it's just a resistor, and the resistor changes over the temperature. But if you only have 100 ohm resistance and you add a cable with 5 ohm resistance, then the accuracy is really low because you add 5% of the accuracy of the resistance, and basically the sensor is really inaccurate if you have long cable length. And in general, the sensors has a really high accuracy. Last but not least, I want to show you some typical applications of calibrated digital temperature sensors. There are many different applications for industrial processes. For example, the temperature monitoring of lasers, melting processes, and the monitoring of welding processes. Also, there are many medical and pharmaceutical applications. Basically, every product is temperature monitored during production and packaging. So, for example, like in incubators. And if you take a look on this picture, you will see the applications for which we sell the most sensors. Mass spectrometers are used in airports or research centers to clearly identify unknown media. So the medium to be measured is dissolved in alcohol, will be heated and electrically charged, and then accelerated. The mass is deflected by a magnet, and the heavier the mass, the higher up it's deflected, and the composition, which we'll get at the end, can be determined from the resulting pattern. And in this application you need really high accuracy. And that's why most of the manufacturers of mass spectrometers are using our sensors, because we have a really high accuracy. Also, there are different applications in environmental monitoring. So, for example, like HVAC, room temperature monitoring using thermostats, or radiator flow temperature, the room climate and humidity as well. And also there are different applications for food industry, for example, like temperature monitoring in cold storage rooms, in packaging of food, like in tinned food, and also in monitoring the cold chain. This was our webinar on digital temperature sensors and how to calibrate them. Thank you for your attention, and now you are welcome to ask your questions.
All right, I can see a few questions already. So number one, how do you secure the supply chain in the event of a crisis, and what was your delivery time during COVID? So first of all, on the one hand, we are very widely positioned and we have the entire value chain in view. And on the other hand, we have more than enough stock for multiple years. So even during COVID, we had a delivery time less than 10 weeks. You meant that a sensor is available in different housings. Would customization also be possible? Yes, absolutely. Like I said in the first slide, we generate over 60% of our turnover with customized products. And for example, like customized probes are possible, or even sensors without any housing. So you could buy a whole wafer if you want to. But we also could adapt the temperatures for the calibration. So for example, if you need a really high accuracy at 40 degrees Celsius, then we could adapt the temperature of at a wafer calibration as well. Can I also buy the wafer or the die? Yes, just like I said, you can buy the whole wafer, or you can buy a few dies for samples, for example. Is it your own product and design? Yes, it is. Usually, in the past, it was the company was called SmartTech, and we bought the company a few years ago, and now we own the product and the design and the manufacturing. Do you also have a I2C sensor? Yes, we could offer an I2C solution. So you could have the advantages of our sensors, and with a converter to I2C, you could have an I2C as an output signal. So we have all the advantages of the duty cycle as an output signal, but you still could use the sensor with a I2C output, because we could add the converter at the end of the cable. So even if you have 5 meters of cable length, you could still have the high accuracy of the sensor. Is there any restrict of the cable length for the SMT172? I wouldn't say so, to be fair. But in the past, we only sold the sensors up to 10 meters of cable length, and it wasn't any problem. So if you want to have a sensor with more than 10 meters of cable length, we could still do some tests, but I personally don't see any problems there. Mm, I know this webinar is not about thermocouple, but I would like to know if a calibration method exists for those sensors. It depends on how you want to calibrate the thermocouples, but in general, that's possible as well, because thermocouples are usually calibrated at 25 degrees Celsius, and it's more or less the same calibration process than we do with our SMT172. So if you have a project behind this, you can still write me a mail and we can take a look on it. Are there any other questions? Someone is typing. Would the temperature sensor with up to 160 degrees also be possible? Yes, it's possible with our new design. So with our new design, you could choose the temperature range between -40 degrees Celsius, even up to 160 degrees Celsius. So I think that's a big advantage compared to the actual generation. So we are trying to develop the sensor to the next step. And with the new generation, that's possible, yes. So you could use the sensor for application up to 160 degrees Celsius. Um, this question is again about the thermocouple, but I'm not quite sure if I answered correctly. So I think it would be better if you could write me a mail and then we can discuss about the solution for the thermocouple. There's one more question coming at the moment. Do you have an example code to read out a digital sensor? Yes, we do. We have evaluation kit and we have an example code for the sensor as well. So if you need it, just write me a mail and I will send you the example code. Okay. I think that's it. I can't see any more questions and no one is typing. So thank you for joining the webinar. I hope it was nice. And if you have any more questions in the future, just write me a mail. Thank you. Bye-bye.